Without anything else, Yash, and also Yash has travelled a long way and has showed great fortitude in getting here, because he's funded himself, and it took a lot of effort on your part. And you're a year late, but no.
Just here? Oh, this one? Just a second, I'll get the pointer as well. Hi, good afternoon, everyone. Today, I'm here to present on my MREST research, Algal dormancy and revivability in space, supervised by Dr. Matthew Davey. And so for my research, I'm focusing on algae for life support systems in space. We know that algae can be used for a lot of purposes, for food, oxygen, even soil production for lunar and Martian bases, if anyone is familiar of Martian. So basically, we can use algae, combine some microbes. A lot of people in Open University at Milton Keynes and Edinburgh University are working on microbes to create habitable soil from lunar and Martian soil. We know that in Martian and lunar soil, we don't have many things which can be used to grow plants. So we can use algae in some microbes to create some sort of habitable soil for plants. And also exploring the possibilities of life in the extremes, the astrobiology side of my project. We know that in space, we have a lot of radiation, solar flares, coronal mass ejections, cosmic galactic rays. And when you're here in Oban, you might be able to see some of them. The beautiful auroras might not be visible at this time, but they are also caused due to coronal mass ejections. And we know that we have radiations at ISS, Moon, and Mars. When we are going from Earth to ISS, it takes us around 2 days. To Moon, it takes us around 3 days. And to Mars, it will take us around 6 months. So if we are planning for a long-term future mission to Mars, we need something we can rely on, which can tolerate 6 months worth of radiation to going to Mars. For that, I'm focusing on cell cycles and pigments of various algal species. My hypothesis is that algae with the dormant phase can be used as seeds and revived later on for long-term space missions. And algae with high pigment content, I mean carotenoids, which are antioxidants, could provide better protection from radiations. As we know that these space radiations causes oxidative damage to cells, and these antioxidants can combine with the free radical oxygens that are produced in the cell due to oxidative stress and can neutralize the effect. So they might offer better protection from space radiations. And extremophilic algae could be better suitable for long-term space missions, as we know that extremophiles have been already exposed to harsh environments, can be salt extreme environment, snow environment, high salinity, high temperature, anything. I'm focusing mostly on 2 snow algal species, Chlorominima and Glyocystis, Hematococcus and Dunaliella salina. Out of them, snow algae are extremophiles. They're found in extreme environments of Antarctica, where we have ozone holes. So I thought that, okay, they have already been exposed to UV radiations from ozone holes. So they might be happy with the space radiations as well. With Dunaliella, it's found in high salt water concentration lakes. So it's already exposed to high salinity extremophilic environment. I thought that if it's going a process of natural desiccation with that high salt, it might be able to tolerate more. And if you're wondering why I'm using Hematococcus, which is not an extremophile along with these species, when we look at different species, starting from bacteria, fungi, even tardigrades that are considered one of the toughest organisms, So basically, when you torture live vegetative tardigrade, just expose it to a little bit of salt or temperature, it will die immediately, the vegetative motile forms. But they form kind of very thick cysts around themselves when they are exposed to harsh conditions. And those cysts can survive for a very long time. With Hematococcus, it's the same thing. The vegetative cells might die immediately, but when they're forming those cysts, they have something in the cell wall, a lot of lipids, a lot of pigments, which will be able to survive for a very long time. I'm working on that side of things. And this is the results that I got. I got a lot of results. So basically, I'm using my algal cells in 2 formats. One, the vegetative phase, the green happy phase, and another one, I would like to call it a special phase. So basically, I did a lot of experiments, optimized my cultures a lot, and managed to produce 2 different cultures. So in this as well, you can see the green culture, which is vegetative, and the orange one, which I produced by experiments and optimization of my strain Dunaliella salina. The orange one is the beta-carotene pigment, which is found in carrots as well. And in my other algal species, as you can see, we have Dunaliella salina with a green phase and an orange phase. Orange is beta-carotene, With Hematococcus, I have a very healthy green paste that you might have seen in the algae lab. Naomi would have shown you. And the red one is astaxanthin. For snow algae 34-1, this is the chlorominima, and it produced tags. Matt have shown you that image in the start with a lot of circular yellow bodies. Those are tags, which might be able to provide better protection. And in 17.3, the snow algae, other species is called Gliocystis, and it produces a lot of EPS, which is very good as well. So basically, in my experiments, I've exposed the algal cells in the desiccated format and in the live cultures to radiations found similar on ISS. Desiccation might be a new way of carrying samples from Earth to space, as we don't need much space for carrying desiccated algae. Otherwise, if you're carrying if you're going to a place and carrying a filled water bottle, it will occupy space. You have to carry much load. Otherwise, you can just carry an empty water bottle, a little bit of powder, add media to it whenever you're going to the moon. So just carry your powder of algae, add some water to it, a packet of mineral from somewhere, and then you'll be able to grow it happily again on moon. These are the live cultures that I use for my radiation experiments. And my radiation experiments were based at CCAP Center for Nuclear Research at Belgium, where they were exposed to radiation dosage equivalent to 3 years on ISS. And these are all the beautiful colors I got from algae. That's why I love working with algae. I love these colors sometimes. And that's all for today from me. Thank you so much. And special thanks to my supervisor for giving me the opportunity to do this work. Also, I think that science is a collaborative work, so I wouldn't be able to do it without the help of everyone else at SAMS. Thanks to Alex, Naomi, and special thanks to Fred as well for helping me all the time, and CCAP, Mikey, for giving me the opportunity as well to speak today. If anyone would like to contact me, I'm more than happy, and I'm ubiquitous on every social media. So feel free to contact me anywhere. Thank you.
I think we have time for a question, so I think there might be one or two mics circulating, or just shout.
Yep, sure. Whoever wants it. Who wants to go first?
So when you expose them to the irradiance, was that all delivered over a much shorter, period than it would have been? So do you think that'll have any effects on the dynamics of it if it's, if it's the same amount total, but it's in a shorter time period?
Yep, of course it will have an effect. So basically I've exposed them for 3 days to a radiation dosage equivalent to 3 years. If we are exposing them to 3 years on ISS, there's no way we can do that on Earth using radioactive isotopes. So that is the limitation of my project, and I've thought about it. But we will be still able to see the effects if they are not being affected by this amount of radiation that they will get in three years during 3 days. I'm sure that they won't be affected during 3 years as well. So if I'm subculturing them, growing them again, and controlling, measuring their statistics with growth curves and metabolic analysis as well using HPLC and GCMS, which later on we are carrying out in May. So we'll be able to see even the minute changes that have occurred in them. And I'm subculturing them again, pelleting them down again, doing the metabolic analysis even on that stage. So I'm sure that if there is a minute change, we'll be able to partially bridge up this gap between the actual radiation dosage of 3 years and 3 days. Hopefully, let's see. Anyone else? Yep, sure.
Thank you. So fantastic work and talk.
Thank you.
Just wondering about, given this fantastic facility that you've got here, are you going to look at the impact of radiation at the genomic level, on the genome? So how the protective environment in the cell protects actually the genetics in the cells from being impacted by them.
So for genomic expression, we thought about it earlier and we were talking about it for a long time, that should we do it or should we not? And unfortunately, it's only 1 year of project and I've already spent a lot of money. These radiation doses were really expensive. So I've spent a lot of money. I'm going to a lot of conferences as well. I'm going to Greece as well at COSPA 2022 to present my results, where a lot of people will be coming. So I might apply for funding from there and try genomic expression later on. But for now, I don't think we have enough money or enough time to
we had to talk Yash out of it.
Yeah.
He was very insistent.
Anyone else? Francisca, you were also. Oh, yeah. Any questions? Feel free to contact me. Thank you. Thanks for listening.